going to now have a look at the parametrics of the different conic shapes. You may recall from last year we've seen the parabola one, and that was 2AP. AP squared was the standard sort of parametrics of the parabola. We'll start off with the circle, I suppose. We don't do a heck of a lot with the circle, but to complete the set of all the conics, let's have a look at that circle. So x squared plus y squared equals a squared, and p is some random point on the circle. The parametric form of that point is defined using the, well, if you like, the polar coordinates, which we saw in complex numbers actually. It's similar to modulus and argument really. We define it in terms of the radius and the angle that it makes at the centre, same as we do with complex numbers. So the x value, I mean, if we wanted to work it out using trig, but we end up with a cos theta, which would be, I guess, the real part of the complex number, and y over a sine theta. So there's actually a very strong connection there between our circle and our complex number. They're the same sort of thing. So a cos theta, a sine theta is the parametrics. And of course, it's very easy to prove that they work, because if I substitute it into x squared plus y squared, I get a squared outside of cos squared plus sine squared, and of course cos squared plus sine squared is 1. So it works. X squared plus y squared will always be a squared. I suppose you could swap it around. You could say x equals a sine theta and y equals a cos theta. It would still work. It just means theta would represent a different angle. And as we're so used to always measuring it to the positive side, we do it in trig, when we're working out slope and things like that. It makes sense to be consistent. So that's why we go with the a cos, a sine. But as I say, it's not wrong to do it the other way. Alright, well, let's have a look at our ellipse and how we define this one. So there's our standard ellipse, and there's our random point. What we do is we draw in that auxiliary circle I was talking about the other day, the one that's got the same radius as the major axis. The mistake that's often made here is drawing the hypotenuse through P, but you'll notice it doesn't go through P. The vertical goes through P. So if you were to draw a vertical up to the circle and then join that point to the centre, now that is of course important because it defines the angle. So if I was to just join the point up to the centre, I would get a different angle. Right, so the angle we're looking for, the auxiliary angle, is the one where we draw the vertical through P and then join that up to the centre. And the reason we do that is something very special happens. First of all, we can work out our x coordinate for the point, and we get a cos theta, same as we did for the circle. But if we were to draw in the smaller circle, and if we were to draw a horizontal from P, it in fact intersects at the smaller circle as well. And so I can get my y coordinate, and we get b sine theta. So it's very similar to the circle, but of course we have a different a and b, one for the major axis, one for the minor axis. So a cos theta, b sine theta. If I was to substitute that into x squared on a squared plus y squared on b squared, the a squareds cancel, the b squareds cancel, sure enough we get cos squared plus sine squared is 1. So it will work every time. Now the sorts of things you may recall that we did was finding equations of tangents, normals, chords, things like that. So let's have a look with the ellipse. So standard ellipse. Now we're going to do it just with the Cartesian coordinates to begin with. So we would differentiate. Now I don't want to waste time and make y the subject of that, so we use implicit differentiation. It's going to be quicker. So we get 2x on a squared, 2y on b squared, dy dx. Again, using the chain rule, implicit differentiation, rate of change, whatever you want to call the idea, it's all the same idea. Rearranging it to get our derivative, minus b squared x on a squared y. So at our random point, which I'll just call x1, y1, then the derivative will be b squared x1 on a squared y1. So to find the equation of the tangent, sub that into our point slope formula. Now, if I get rid of the fraction, so multiply everything by a squared y1, expand out on the right hand side, and I've rearranged it So it sort of matches your notice. I've got b squared with the x's on the left and b squared with the x's on the right, and so on. But what I'm going to do is divide everything by a squared b squared, because it makes it more obvious now, the right hand side. So I've got x1 squared on a squared plus y1 squared on b squared, but I know the value of that because x1 y1 is on the ellipse. Therefore it must satisfy the equation of the ellipse, so it must equal 1. So on the right hand side, that's just 1. And we get the equation of the tangent. Now the beautiful thing is, the equation of the tangent mimics the equation of the ellipse itself. It's just that instead of having x squared on the top, I've got x times x1. Well, if you sort of pretend that number 1 is not there, x times x is x squared. And y times y, and the other one is y squared. So it actually mimics the equation of the ellipse. So it makes it a very easy thing to remember. I mean, if you've got the equation of the ellipse, finding the equation of the tangent, we know it's going to mimic that equation. The normal, I'd like to say, was just as nice. There's still a lovely relationship. Let's see what happens. It's just not quite as nice as the other one, I don't think. So invert, negative inverse, sorry, for the slope. Multiply out. Now this time, I'm going to divide everything by x1, y1. Now why do I want to do it that way? Well, if you have a look at this one, what I've basically done, if you have a look at the coefficients of x and the coefficients of y, with the tangent and the normal and compare them, they're the reciprocal of each other, but the sign in the middle has changed. Well, that makes sense, because remember the slopes are the negative inverse of each other, and it's the coefficients of y and x that forms the slope. So if you know the equation of the tangent, those coefficients are easy on the normal. Now, equals a squared minus b squared. And you think, oh, what's that? A squared minus b squared actually is something quite clever. It's a squared e squared. Remember our formula we had for finding b squared? And I said one of the ways I like to think about it is make e squared the subject, and I had e squared was equal to a squared minus b squared over a squared. Well, if I multiply both sides by a squared, so it's actually the foci squared, or the x coordinate of the foci squared for the normal. So there is a nice relationship there. Okay, what happens if I use parametric coordinates instead? I can sub straight into the derivative. I've already worked out the derivative, but now the x value is a cos theta, the y value is b sin theta. Now I'm not going to change that to cotan, the cosines are very tempting, but I'm not going to. Because when we sub into tangent, now I'm going to multiply everything by a sin theta and expand out. And you'll see why I didn't bother making it cotan, because I now end up on the right hand side with a lot of sine squareds and cos squareds. And sine squared plus cos squared is 1. So on the right hand side I just have AB, but I'll divide by the AB, and I get the x cos theta on A plus y sin theta on B is equal to sine squared plus cos squared, which is 1. But again, remember what we saw before, it mimicked the equation of the ellipse. It was x1 on a squared. Well, the x coordinate in this case is a cos theta. So all it really is substituting a cos theta into that. The a's cancel and you get x cos theta on a, and so on. So we should see a similar thing happen with the normal, but let's actually derive it. And a squared minus b squared, divide both sides by sine theta, and so again we get that relationship of equals a squared minus b squared, which is of course a squared e squared. Okay. Now here's the unfortunate thing. Come to the exam and they give us our resource sheets. They give us a resource sheet for 2 unit, they give us a resource sheet for 3 unit, and on 3 unit they have all the parabola ones, lovely, but they don't give us a resource sheet for extension 2. So we're going to have to remember these. Okay. Do I derive them? Only if they specifically have asked me to. Only if they specifically have. And I guess you can have a look at how many marks a question's worth. It gives you a bit of an idea as well. as whether you would do that. So a reminder, here's put it all together on one page. Sort of highlight a bit more. There it is, look, x squared on a squared plus y squared on b squared equals 1. The tangent is x1x on a squared, y1y on b squared, pretty much the same sort of thing. And the normal, okay, those coefficients, let's turn them upside down, change the sign. Equals a squared minus b squared, but I prefer to think of it as a squared e squared, nice and neater. And in parametric form, we get that. All right, let's do an example where we actually do have to. So if it says find the equation, then okay, we got to derive the thing. Okay, we actually got to work it out. We haven't got a choice. So all right, differentiate implicitly, minus x on 16y. We're at the specific point of 2 minus root 3 on 2. Slope turns out to be 1 on 4 root 3. It really is no different to any other find the equation of the tangent question. I've got the slope, I've got the point slope formula, expand out, voila, we get an answer. Find the equation of the normal. Now they've given us in parametric form and they've told us what theta is. Yes, you could substitute theta equals pi on 6 on and get the Cartesian coordinates and go with that. But it's easier to work with the parametrics, I think. And a reminder, when we're going to need this, because if we're going to differentiate the parametrics, I'm going to end up differentiating sine, differentiate sine, you get cos, differentiate cos, you get minus sine. So here's the nice thing about the parametrics. I can straight away go, well, if x is 2 cos theta, dx to theta is minus 2 sine theta, y is sine theta, dy to theta is cos theta, so straight away I get dy dx is cos theta on minus 2 sine theta. Now I'm going to work out, because they've told us specifically that theta is pi on 6. So sub in theta equals pi on 6. We get a slope of minus root 3 on 2. And now I'm going to substitute in for the 2 cos theta for the x value and the y sine theta. And voila, we get again an answer. Let's look at something a little bit more interesting. Show that if y equals mx plus k is a tangent to the ellipse, and it's our standard ellipse, then this relationship, a squared m squared plus b squared equals k squared. Okay. There's lots of different ways of doing this. So how do I do it this time? I said, well, I'm going to play with the parametrics. X is a cos theta, so dx to theta is minus a sine theta. Basically, I'm just going to derive the slope here. So dy dx is minus b cos theta on a sine theta. Now, if y equals mx plus k is the tangent, then we know the derivative must equal the slope of the tangent. So dy dx must equal m. So m is now minus b cos theta on a sine theta. That gets me a little relationship. Okay. So that's one relationship. So that's using the idea that the derivative must equal the slope of the tangent. The second idea that I'm going to use is that, hang on a sec, if the tangent meets the ellipse at the point a cos theta b sine theta, then a cos theta b sine theta lies on the line. So it must satisfy the equation of the line. So b sine theta, the y value, must equal m times a cos theta plus k. And I'll rearrange that and get a second equation. Now if I square the first one and square the second one and add them together, look what happens. I get a squared m squared sine squared plus cos squared, which is 1. The middle, the 2ab m sine theta cos theta, cancels. And I get b squared sine squared plus cos squared, which is 1. And there's our result. A squared m squared plus b squared is equal to k squared. That's just one way of doing it. I suppose other ways you could involve the discriminant. You could say, oh, well, hang on, I know if it's a tangent, when I solve these things simultaneously, the discriminant equals 0, and you could come up with other ideas that way. Let's talk about the chord of contact. Now, you may remember, I hope, chord of contact, you've got the external point. You draw 2 tangents to the shape, and where they meet the shape, the chord between them is the chord of contact. So T is my external point, x naught, y naught. I can draw the two tangents in. Now, let's say it meets at the point P, and P has coordinates x1, y1. Then I know the tangent at P, from what we just saw, it would end up mimicking the ellipse. So it'll be x1, x on a squared plus y1, y on b squared is equal to 1. And the tangent at Q, let's call that the point x2, y2, it would have the equation x2, x on a squared, and so on. Okay. But T, x naught, y naught, lies on both lines. So it must also satisfy both of those equations. So it must be true that x1, x naught on a squared plus y1, y naught on b squared is equal to 1. That must be true. And it must also be true that x2, x naught on a squared plus y2, y naught on b squared is also equal to 1. We're trying to find the equation PQ, the equation of a line that when I substitute in x1, y1, it works. When I substitute in x2, y2, it works. Now, the equation of a line will be some constant times x plus some constant times y is equal to some constant number. So P and Q must both lie on a line with this equation. Because if I substitute in x1, y1, I get this statement here with the blue tangent, which I know to be true. And if I substitute in x2, y2, I get the statement that we came up with the green tangent. So we know it works. It looks like I've cheated. It looks like I haven't done any maths, haven't done any deriving. And I see you nodding your head in agreement. But it's the quickest way of working it out. But what does it mean? It means that the equation of the chord of contact mimics the equation of the tangent, which mimics the equation of the ellipse itself. But think about it, it must be true. Why must it be true? Your chord of contact, so you've got an external point and it's got two tangents. If you get that point and bring it closer and closer and closer to the ellipse, the two tangents are going to get closer and closer and closer together until that external point touches the ellipse. You're no longer going to have a chord of contact. You're now going to have a tangent. So of course it must have the same equation as the tangent. So x naught x on a squared plus y naught y on b squared equals 1 is the equation of our chord of contact. Time to play.